So we're going to look at the activation energy and how this affects the rate of reaction, and also try and put some maths into this by using the Arrhenius equation. So first of all, we need to consider why the rate of reaction increases as the temperature is raised. Well, at higher temperature, the reactant molecules will be moving more quickly, and therefore they will collide more frequently. This will result in an increased rate of reaction. However, the increase in reaction rate with temperature is much greater than can be explained by this factor alone, so we must consider another process operating. So by using a little bit of maths, we can calculate how many collisions take place between reacting molecules per second. And if we do this at ordinary temperatures, it turns out that the collision rate is enormously large. And so if each collision led to a successful reaction, then all reactions would be completed almost instantaneously at ordinary temperatures. But as we know, this does not happen in reality. So it must mean that not all collisions actually lead to a successful reaction. Most colliding molecules simply don't have enough energy to react and just bounce off each other. We know from RAS chemistry that energy is needed for the molecules to break their old bonds before new ones can form. The minimum amount of energy necessary for this is the activation energy, and this is shown in the diagram with the Maxwell-Boltzmann distribution. At higher temperatures, a greater proportion of molecules have the required energy. So we can see in this shade area here how an increase in temperature affects the number of molecules that have an energy greater than the activation energy. So this was all discussed at AS chemistry, so you should be quite familiar with the Maxwell-Boltzmann distribution. Now moving on to some A2 chemistry, the Arrhenius equation, which is shown in red, shows the relationship between the rate constant, which is little k there, and A, which is the pre-exponential factor, that is a constant. E is the base of natural logs, and this capital E here is the activation energy. R you would have come across before at AS chemistry, that's the gas constant, and T is the absolute temperature, and you must remember to convert in Kelvin. The pre-exponential factor is a constant for a particular reaction, which shows the rate of potential successful collisions occur. Some collisions, because of their geometry, will never be successful, regardless how much energy those particles have. This expression here is a fraction of molecules which possess the activation energy or more. When multiplied together, we get the rate at which successful reactions occur, and that is the rate of reaction. So this equation shows us how to calculate the rate constant and how the rate of reaction will therefore vary with temperature. More commonly, however, you don't use the expression in this form, and you're given data on the rate constant for a reaction at different temperatures and asked to show this information on a graph. So let's look at that. Okay, so here we've taken the Arrhenius equation and we've taken natural logs of both sides. If you're not a mathematician, don't worry about it, but you will need to know both forms of the Arrhenius equation. If you have a look at this and you remember back from your GCSE days, this is in the form of y equals mx plus c, which is the equation for a straight line. So if I plot the log of the rate constant against 1 over t, I will be able to calculate both the natural log of a, and the gradient will be minus e over r. Now sometimes when you plot this graph, and we'll look at an example a little bit later on, it does freak people out because you will have a negative gradient. But if you think about it, it's got to be a negative gradient because the activation energy is going to be positive, and we know that the gas constant is positive. If when you plot this and you get a positive gradient, then you've done something wrong. So think again and redo your calculations. So in this table, we've shown the temperature and the rate constant at various temperatures. Now notice the temperature is in degrees C, but you must convert that into Kelvin here. So the first thing to do is calculate the temperature in Kelvin. Okay, now when you go to when you then take 1 over T, you will get very small numbers, and log K will be negative like so. So when you plot that, and you will get a graph like this, you can see that you will have a negative gradient. The gradient will be -5 divided by 0.00037, and the y-intercept will become log A. So if you times this number by the rate, the gas constant, and also by -1, you will find your activation energy. Just in case you're wondering, for these numbers here and also for these numbers here, there's been a bit of a formatting problem. It should be 1.1 times 10 to the -3 for the first one, and 2.11 times 10 to the -3 for 1 over T. It's just you've got a dash where there should be a multiplication sign.